we have discussed yesterday. So ultimately, the purpose of the task of a control engineer is to design a controller that will meet certain specification. So normally specification will be given in terms of time constant, damping ratio, percent overshoot, and things like that. So we want to be able to choose the value of proportional controller gain K that can meet that specification. So here we are going to perform that task. So using this root locus diagram. From the root locus diagram, we can anticipate, we can predict the behavior of the system or how the system is going to respond based on the dominant roots of the system. The dominant roots are the roots that are closest to the imaginary axis. The roots which is further away from the imaginary axis, it is called the non-dominant roots because that root will produce a very short time constant, a very small time constant. So the response because of that term will die out quickly. So we are going to predict or approximate the behavior of the system based on the dominant roots. Normally, we're going to have two complex roots, which is closer to the origin. And for a selected value of K, so we will know the location of the roots. Once you know the location of the roots, so just based on the dominant root, the time constant is 1 over the real part of the root. So the real part of the root will give us the information about time constant. So 1 over the real part of the root is going to give us time constant. The imaginary part of the root is going to give us the information about the damped natural frequency. And then the distance of the roots of the selected root to the origin will give us the information about the natural frequency. And then if you draw a line from the roots to the origin, and you're going to have this angle beta, that angle beta is going to give us information about the damping ratio, which is the cosine of that angle is going to be equal to the damping ratio. So keeping that in mind, so we are going to go to our second example today. Example 318. Okay, so we are given this system, a third order system to be controlled with proportional controller gain K, and then we have a unity feedback loop. So the system to be controlled is 5 divided by S, and then there's a factor 0.25 S plus 1, 0.1 S plus 1. So when we draw the root locus diagram, we want it to be in a form of zero pole format. But anyway, the first look at the question. Choose or select the value of controller gain K. So we want to design the value of K such that the maximum damping ratio is 0.5. So we don't want the damping ratio to go above 0.5. And the maximum value of time constant is 1 second. So that is the specification. So our first task is to draw the root locus diagram. From that, and then we can see whether we can meet the specification or not. To draw the root locus diagram, you need to extract the open loop transfer function and then put the open loop transfer function in a form of zero pole format, not 1 plus time constant S like this. So this is 1 plus time constant S, 1 plus, so 0.25 is another time constant S. Anyway, the first task is always extract the open loop transfer function. The open loop transfer function is just the loop gain, which is k multiplied by the transfer function multiplied by h. H here is 1. So the open loop transfer function is kgh, which is 5k divided by the denominator. And then we need to transform this into zero pole format. Or you just multiply everything, the numerator by 200, multiply by denominator by 200, and you get that zero pole format. And now I'm going to replace 200k with k prime to make sure that it's going to make our life easier when we draw the locus diagram. So now we are going to draw the locus diagram when k prime, which is k prime is equal to 100k, when k prime start from 0 to infinity, and then we can draw the locus diagram. To draw the locus diagram, we need to go through all the nine steps that we have discussed before. Okay, so we are going to draw the locus diagram when k prime start from 0 to infinity. So we locate the 0 in poles. So there's no zeros. In the numerator, there's no s. So we have 3 poles, 1 at the origin, 1 at -4, 1 at -10. So we have 3 poles, no 0. So when you have 3 poles and no 0, you're going to have 3 asymptote line. And of course, asymptote angle for 3 asymptote line is 60, 180, and 300, because they are symmetrical about the real axis. And then you can now compute the intersection of asymptote line. We have a formula for that. Today is not the discussion of that. We have discussed that so many times. And then in this case, okay, so let us stop there. So let us stop at this intersection line. So now we can now partially draw the locus diagram. Now we already have this intersection of asymptote. Okay, so first is locate the 0 pole. Let's go to the diagram. So we have 3 poles, 1 at the origin, so put an X there. Another one at -4, put another X there. And then there's another pole at -10, put another X there. On the real axis, the locus exists to the left of odd number poles and 0. So this is the first pole. To the left of first pole, you're going to have locus on the real axis. To the left of even pole, you're not going to have locus to the left of even pole. And then this is your third pole. To the left of third pole, you're going to have locus as well, all the way to infinity. So that is on the real axis. And then we know that the locus start at the pole. So this is going to go all the way to infinity, the third pole. But from origin to -4, because we don't have any 0, our locus is going to end up infinity. Therefore, there is going to exist a breakaway point between the origin and -4. Okay, so therefore, you need to compute the breakaway point. How do you do that? Okay, never mind. Let's talk about how do you do that next in a while. But we can now draw the asymptote line. So the intersection of the asymptote is at -4.67. So this is the intersection of asymptote. Every asymptote line is going to go through that point, -4.67. So the first asymptote angle is at 60 degrees. So you measure 60 degrees and draw a line, a straight line. Draw a straight line through point -467, which is the intersection of asymptote. The second asymptote line is at 180, it's all the way to the left. And then the third asymptote line is symmetrical with the first asymptote line. So in this case, I only draw the top half of the root locus diagram. And because it is symmetrical, so in this case, there's no point of drawing the lower half of the diagram. Okay, so the blue line here is the asymptote line. We know eventually our locus is going to approach that line, this asymptote line. But now we need to compute the breakaway point between origin and -4. How do you do that? If you remember correctly, so this is a breakaway point. You just rewrite the characteristic equation in terms of k and differentiate that with respect to s equals 0, and you can solve for the breakaway point. Today is not the day that we compute the breakaway point. We have discussed that so many times already. So after you have done that, you're going to get a breakaway point, the value of breakaway point at -1.76. And then, so this is -1.76. You know that your locus is going to break away at that point, and it's going to leave the real axis at 90-degree angle. It's going to go straight up, and then finally it's going to approach the asymptote line. So we need to compute the intersection of our, so we know that eventually it's going to go, it's going to approach this asymptote line, and when k is getting bigger and bigger and bigger, you're going to go to the left, to the right of imaginary axis. But you can compute the intersection with imaginary axis using the Routh stability criterion. We have discussed that so many times already. So when you do that, you're going to get the intersection with asymptote line happens at -6.32, plus and minus because it is symmetrical, 6.32. So you go back to your drawing. So that is your intersection with the asymptote, intersection with imaginary axis. And now you can now draw your locus diagram, leaving the real axis at -1.76, goes straight up at 90-degree angle, and then you must go through, turn to the right, and you must go through point negative, you must go through point 6.3, and then go all the way, now approach your asymptote line. So that is how you draw your locus diagram. Okay, so that is the first part of the question. Draw the locus diagram. Normally you can earn 6 marks out of that. 6 marks already. Even though you cannot answer the question, this is even though you cannot answer what value of k that can satisfy the specification, you can score 6 marks already. That's already passed. You don't have to repeat this class again. All you have to do is draw the locus diagram. You get 6 points without even answering the next question. Okay, but okay. Let's move on. So the question want us to select the value of k such that it meet the specification of damping ratio and time constant. Okay, so we know that when k is equal to 0, your locus start at the pole. When k keep increasing, and then it's going to go from the origin, it's going to go to the left, and then it's going to break. As k increases, increases until to infinity. So that is the path taken by the roots. All possible paths taken by your roots when k is increased from 0 to infinity. All right, so now let us answer this question. So the specification is the damping ratio must not be greater than 0.5. The time constant must not be greater than 1. Okay, so now from that information, so we can now, so let us just choose this damping ratio 0.5. So for damping ratio 0.5, we get the angle beta must be equal to 60 degrees. So you come here, and then you, from the origin, you measure 60 degrees, and then you draw a straight line A here. Anywhere below that, so this is going to give you the damping ratio of 0.5. Okay. So when damping ratio is 0.5, the angle beta is 60 degrees. So you draw a line from the origin at an angle of beta 60 degrees. So this line AA, this line represents a damping ratio of 0.5, and you don't want to go above that. You don't want to. You don't want your damping ratio. You don't want your damping ratio to be above 0.5. So if the angle beta falls below 60 degrees, and your damping ratio is going to increase. So you want the root to be located above this AA line. Anything above this AA line, this blue line from the origin at 60 degree angle, any point above this line is going to satisfy the requirement that the damping ratio must be less than 0.5. See, the maximum damping ratio is 0.5. So we want damping ratio to be smaller than 0.5. So this is the critical angle of 60 degrees. And our roots must be either on that line or above that to give a damping ratio of equal 0.5 or less. So that is the first specification. The second specification is the time constant should not exceed 1 second. So 1 over the time constant is going to give you the imaginary part of your, the real part of your roots. Okay, from your second specification, for time constant equal 1 second, so zeta omega is 1 over time constant, so 1 over 1, you get 1. So for a time constant of 1 second, the real part of your root must be equal to 1. Anything less than that is going to produce a time constant bigger than 1. So this is the critical point that will give you time constant of 1 second. So the real part of the root, zeta omega n, should not be less than 1 second, should not be less than 1. Let's go back to our diagram. So this is now, look at my scale. So this is -2, that's -4. So this is -1. And you draw a vertical line, go through -1, because that's the real part of the root, -1. We don't want the real part of the root to be less than 1. The magnitude should be less than 1. So you draw a straight line up. So this is the line BB here, B from -1 vertically up. This line BB represents time constant equal to 1. Anything to the right of line BB here is going to give you time constant of B greater than 1. So to meet the specification, the roots must lie to the left of this vertical line BB. Okay, so anything to the left of line BB will now meet the specification. Anything above line AA is going to meet the specification. So you can select any roots from line AA to line BB. Anywhere here will satisfy the specification. Now you can now select any point between here to there. For simplicity, I just select that point. So this is for simplicity, selected root location, but you can select any point above that up to the vertical line BB. Those will meet the specification. But for simplicity, let us just select that for zeta to be equal to 0.5. When zeta is equal to 0.5, it also satisfies the requirement that the time constant should not exceed 1 second. So this point will satisfy the specification. Or you can select any other point, just a matter of preference. You can select a maximum of the point exactly on the vertical line BB. So any point between that can satisfy the requirement. The next question is, what is the value of K for your selected point? what is the value of k here? We know that the value of k here is 0, so it's going to increase, and the value of k when the locus crosses the imaginary axis is when the system becomes marginally stable. You can get the value of k from your Routh table. But now, what is the value of k here at your selected point? So you can compute the value of k using the magnitude criterion. Every point on the locus must satisfy the magnitude criterion. Do you still remember what is magnitude criterion? What is magnitude criterion? Do you still remember that? Let's go back. No, this one. Probably this one. Nope, nope. There, here is the magnitude criteria. The magnitude of the open loop transfer function must always equal to 1. So the magnitude of kgs for any point s must always equal to 1. So we're going to use this criteria to compute the value of k. Okay, so let's go back to our diagram. So the magnitude criteria says that the magnitude of kgh must be equal to 1. So this is a magnitude criterion. When we select that point, so the open loop transfer function is the kgh is this. So k prime divided by s, s plus 4, s plus 10. So the magnitude of that is just the magnitude of k, magnitude of s, magnitude of s plus 4 and s plus 10. Okay, so yes, the magnitude of kgh is just k prime. K prime is a constant. So the magnitude of the roots, the magnitude of s plus 4, the magnitude of s plus 10. So how do you get this value? Magnitude of s plus 4, magnitude s plus 10. So you go back to your diagram. So this is your s. So the magnitude of s is just from the origin to your point. So you measure that. So this is the magnitude of s. So you measure the distance from the origin to your point. So that will give you the magnitude of s. Now s plus 4 is the same. So this is the magnitude of s plus 4. This is just a vector, the magnitude of a vector. So you can imagine the 4 plus s. This is negative 4. If it is a positive 4, so you go to the right, 4 plus s, and this is the magnitude of 4 plus s. The distance from negative 4 to your point s is going to be the magnitude of s plus 4. You can measure that, or you can compute that as well. If you draw this to scale, you can just measure that. So I measure it to be 3.5. So the magnitude of s is 2.9. And then we need another one, s plus 10. This is s plus 10. So s plus 10, you start from 10. You go from negative 10 to origin, that is going to be 10. And then this is s. So 10 plus s. So the magnitude of s plus 10 is just the distance from negative 10 to your roots. So you can measure that if you draw your diagram correctly and make a measurement. So I measure that to be 8.9. So this is the magnitude of s is 2.9. S plus 4 is 3.5. S plus 10 is 8.9. Where do I get that? I measure using, because I have drawn this to scale, so I can measure that and then use my scale, and then I can compute the distance. So with all these values available, you can now calculate your gain K. Okay, so this is S 2.9, S plus 4, 3.5, S plus 10, 8.9. So these values are from your drawing, your diagram. You measure that using a ruler. And from there, this must satisfy the magnitude criteria, which is equal to 1. And then you can now compute K prime, approximately 90. And from there, you can now compute K, which is equal to 0.5. Okay, so here I have a note here. Note that the value of magnitude of S, S plus 4, and S plus 10 are measured from the root locus diagram. So now this is the second part of your question. So answering this question, you're going to earn another 4 marks. Okay, so that is how you estimate the value of your controller gain K from your root locus diagram. All right, so do you have any question? In fact, my notes here is quite self-explanatory. Okay, so yeah, you can read this, and even you don't have to attend my class. You just go to the e-learning and download this, and you can read it on your own. There's nothing to it. Probably you fall asleep already, right? Do you have any question? Okay, you can go to your e-learning and download your assignment, and then you can start working on your assignment. Well, if you don't have any question, then okay. So do we need to draw the locus diagram in real scale, since the value of magnitude must be measured? Duh. You will be in your test. You normally, when you take your test in examination hall, you will be given a graph paper. You need to draw this to scale. There is a must. You will be given, but since you're going to have your online test, make sure that you have the graph paper ready to make your life easier. It must be drawn to scale, and you must use the same scale for imaginary axis and the real axis. For example, how about sketch? If you compute the critical value accurate enough, if you compute this value, all this value accurate enough, the intersection of asymptote, the breakaway point, the intersection of imaginary axis, your drawing is going to be quite accurate. But make sure that you use the same scale for imaginary axis and the real axis. If it is 1 centimeter for 1 unit for imaginary axis, you must use 1 centimeter 1 unit for your real axis as well. Otherwise, the angle will be meaningless. See, the angle 60 degrees will be meaningless. Of course, you need to draw that using the graph paper. Any other question? No more? All right, that's good. That's great. Is a breakaway point is used to determine S? No. No, 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 no. No, 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 no. The breakaway point is to determine the point where the locus leave or enter the real axis. So this is the breakaway point. So the root S is selected based on the specification. So the route that you select must be on the red line. That's one of the criteria. And then to meet the specification, so you draw these two straight line, AA for damping ratio 0.5 and vertical line BB, that is for time constant equal to 1. And then you can select any point S between those two lines. The breakaway point, we use the breakaway point to draw the point where the locus will leave the real axis. What intersection? No, the breakaway point is not the intersection. It's the point where the locus leave the real axis. The intersection with imaginary axis is different from the breakaway point. The intersection of imaginary axis, you get this from the Routh table. Any other question? You will get this when you will understand more about this when you start working on your assignment. Okay, so that's it. That's it from me. So I'm going to end my presentation. If there is no more question, go to your e-learning and download my notes and the assignment 3. So have a nice weekend.